Energy from the void? Why official science recognized Google's failure in 2025. At the beginning of 2025, within the walls of the Google Corporation headquarters, an event occurred that was supposed to overturn our understanding of humanity's energy independence. A group of leading physicists working under the patronage of the tech giant completed a multi-year cycle of experiments searching for low-energy nuclear reactions. The results, published in the authoritative scientific journal Nature, caused a wave of disappointment in broad circles. However, for a thoughtful researcher, they became only a new chapter in the long history of studying the hidden processes of matter. Recent evidence reveals that behind the facade of official failure hide unresolved questions that force the academic community to revise the fundamental laws of thermodynamics. We stand on the threshold of a moment when old textbooks stop providing answers to the challenges of modernity. Scientific debates continue around why a project costing tens of millions of dollars did not lead to the creation of a working prototype of a home reactor. The official report states that researchers failed to achieve stable excess heat generation that could be unambiguously interpreted as the result of nuclear fusion. Nevertheless, test protocols point to strange anomalies in the behavior of hydrogen isotopes inside the palladium lattice, which do not fit into standard models of plasma physics. This experiment became the most large-scale study in the field of cold fusion over the last 35 years that have passed since the scandalous statement by Martin Fleischmann and Stanley-Pons. Why then, despite colossal computing power and access to the purest materials, did the result turn out to be so ambiguous? To understand the context of the events of 2025, we must return to the end of the 80s of the 20th century. Back then, two respected chemists stated that they were able to obtain the energy of the stars in a simple glass flask at room temperature. The world froze in anticipation of cheap and infinite energy, but the criticism that followed and the impossibility of rapid replication of the results turned the term cold fusion into a synonym for pseudoscience. However, recent evidence reveals that many laboratories around the world continued these studies in a mode of strict confidentiality. In 2024, the Massachusetts Institute of Technology published a series of works indicating the possibility of locally overcoming the Coulomb barrier in the crystal lattices of metals. These studies show that the problem might have lain not in the physics of the process itself, but in the imperfection of the tools for observing the microworld. Standard particle detectors often turn out to be blind to processes occurring on scales of several angstroms inside a solid body. In recent years, scientific debates have continued around the hypothesis that collective electron effects can shield hydrogen nuclei, allowing them to approach each other at critical distances. This assumption calls into question the dogma about the necessity of giant temperatures and pressures for carrying out a nuclear reaction. If this is confirmed, then the entire history of energy over the last decades will appear before us in a completely different light. The Google Corporation experiment in 2025 was aimed at testing precisely these boundary states of matter. Scientists use the most complex systems of electrolysis and gas saturation, trying to reproduce the conditions under which anomalous thermal effects arise. The equipment occupied a space with an area of more than 500 square feet, about 46 square meters, and was equipped with the latest generation of sensors. Despite careful preparation, the system did not produce the expected cascade of energy that could power even a small building. In official circles, this was perceived as the final sentence for the dream of cold fusion. However, specialists from the University of Maryland who participated in the data analysis noted in their reports for 2026 the presence of strange isotopic shifts. In the spent palladium samples, traces of elements were discovered that should not have been there according to the laws of classical chemistry. This indicates that nuclear processes were indeed occurring, but their intensity was extremely low for practical application. A logical question arises as to why, in the presence of signs of a reaction, the system did not switch to a self-sustaining fusion mode. Perhaps we still do not understand some key parameter that acts as a catalyst in these hidden systems. While private corporations record failures, state institutions demonstrate a more cautious but optimistic approach. In 2024, the Glenn Research Center, belonging to NASA, presented results on so-called lattice-confined fusion. Unlike Google's approach, NASA engineers focused on using erbium saturated with deuterium and irradiating it with a stream of high-energy photons. Their data indicates that under certain conditions, deuterium nuclei can fuse, releasing neutrons and heat, even without extreme heating of the entire system. This direction received the name of low-energy nuclear reactions, or LENR for short. Scientific debates continue regarding whether these laboratory successes can be scaled to the level of industrial installations. Researchers from NASA claim that the key lies in the geometry of the crystal lattice and the dynamics of atomic vibrations within it. If one imagines the atomic lattice as a huge orchestra, then to start fusion, all instruments must sound in perfect resonance. The slightest deviation in material purity or temperature leads to the damping of the process. This explains why the 2025 experiments at Google could have been failed due to microscopic defects in the structure of the electrodes used. We are dealing with a technology that requires precision going beyond the limits of modern manufacturing standards. There is also a second scientific hypothesis put forward by the Smithsonian Institution at the beginning of 2026, which links anomalous heat generation with weak interaction processes. According to this theory, under certain conditions, electrons can be captured by protons, forming ultra-cold neutrons, which are then easily absorbed by neighboring nuclei. This process is not fusion in the classical sense, but it is capable of releasing a significant amount of energy without dangerous radiation. If this hypothesis is correct, then we were looking in the wrong place, trying to collide nuclei head-on, while nature offers a more elegant path for the transformation of matter. Recent evidence reveals that similar processes can occur even in biological systems, although this statement still causes fierce disputes in the academic environment. Research from the last 2 years shows that the boundary between chemistry and nuclear physics is much more blurred than we were taught in schools. We are used to separating these worlds with huge energy barriers, but nature itself constantly finds ways to bypass these obstacles. Perhaps Google's failure in 2025 will become that very necessary lesson that will force scientists to change their paradigm and stop storming the fortress where a side gate is open. The history of cold fusion is not just a chronicle of scientific discoveries and disappointments. It is a mirror of our society and its relationship to the unknown. We see how large institutions and corporations try to tame the energy of the future using the methods of the past. However, a true breakthrough often occurs not within the walls of sterile laboratories with billion-dollar budgets, but in the minds of those who are ready to question established dogmas. Every new study, whether successful or not, brings us closer to understanding the true nature of reality. We need to develop in ourselves the ability to analyze primary data without relying exclusively on the interpretations of officials. The call for independent investigation and intellectual autonomy is more relevant today than ever. Recent evidence reveals that the world of science is full of unresolved questions waiting for their discoverers. Do not let loud headlines about failures lull your curiosity and thirst for truth. We live in an era when information is available to everyone who is ready to spend time on its study and comprehension. Explore NASA reports, read publications from the Massachusetts Institute of Technology, and draw your own conclusions about the direction in which our civilization is moving. An energy revolution may begin not with a new flash in a reactor, but with a change in our consciousness. Concluding this investigation, I want to emphasize that the failure of the 2025 experiment is not the end of the road for low-energy nuclear reactions. On the contrary, it is an important signal that we have approached the very edge of our current understanding of physics. Scientific debates continue, and in them, a new picture of the world is being born, where matter and energy are connected much more closely than we could have imagined. Ahead of us lie new discoveries that will perhaps be made in the next few years. Be vigilant and maintain a critical mindset, for the truth often hides in those places where others are afraid to even look. Our journey into the depths of the mysteries of matter is only beginning, and each of you can become a participant in it.